right, chapter 19.
Hey, Josh.
Hi, Josh.
Magnetic poles.
Parts of a magnet where the magnetic effects are strongest are called poles. Magnets have a pair of poles, a north pole and a south pole. A magnet's north pole always points north, and its south pole always points south. Poles that are alike repel each other. For example, two north poles repel one another. Likewise, two south poles repel one another. However, two unlike poles, north and south, attract one another.
It wasn't quite long enough. I'm trying to find some paper clips.
Temporary magnetism.
What's that?
Do they include temporary magnetism in this section?
Yes. In fact, we'll do a little bit with temporarily magnetizing those things. How do magnets work? Well, this is our understanding. They are magnetic domains. If you look on your book on page 665, there's a diagram there on the top right-hand side. Magnetic domains. So there are small regions composed of a group of atoms whose magnetic fields are aligned in the same direction. So these small regions are these magnetic domains. And if you look at picture A up there, the blue arrows in the direction that a north pole would be pointing. And so they're randomly oriented in most substances, these magnetic domains. And things that have magnetic domains, we call them ferromagnetic materials. Typically it means they're going to have some iron content in them. Though there are some composite materials that don't have to have iron. But naturally they're going to have some iron content in them. So that top one up there is just going to be a piece of ferromagnetic material, some material that has iron content, where the domains are just randomly oriented. And so we don't have, thank you, a magnet. But the bottom one, we've lined up those magnetic domains. And when they're all lined up in the same direction, then that material becomes a magnet. So how do you line up the material in those magnetic domains? Any ideas?
Wait, so is that talking about even like a refrigerator magnet?
So a refrigerator magnet would look like that bottom one. The magnetic domains are all pointed in the same direction, so it acts like a magnet as the whole. Any ideas how we can line up possibly those?
External magnetic fields?
Excellent reading. External magnetic field. Right here I have some rocks. Now you might notice they kind of look a little shiny on the surface there, so they obviously have some content that's just not like the flint rocks that are right out there. But these, see if I can hold it down far enough for you to see. These are magnetic. Lodestone is the name of it. So how did these rocks get magnetic? What external magnetic field caused them to become a magnet? Can you think of any external magnetic field that rocks may be in, even those rocks sitting out there don't have iron? The Earth. The Earth. The Earth's magnetic field. That is the external magnetic field that has lined up the domains of these lodestones, these ferromagnetic rocks, these rocks that have enough iron content in them that they become a magnet.
So pretty much if you're around a strong magnetic force for a long enough time, it becomes magnetic itself?
Correct. It will do that.
Is it just a metal parts?
You've got to be a material that has, we call them ferromagnetic, and generally that means they have iron content in it. So yes, if I took a piece of plastic or paper, no, can't magnetize that. What this is right here is simply a magnetic field that I can put something in to magnetize it. Now, my problem is all my things are magnetized that I have. All my metal things that I have laying around are magnetized, including this nail that's sitting out here. It's already magnetized. Can you see the, I don't know if you can see the, it's spinning. A key?
Yeah.
Probably doesn't have iron in it.
Can you demagnetize them?
So you can work on demagnetizing things, is exactly right. This one happens to fit real nicely right here. And it has, where is it? This side, there you go. You can see south pointing down, north pointing down. So, written on the ends of it there. Put it in there, we'll turn it on, and then I just push this button. In fact, let me see if I can tip it to the side a little bit, see if it'll be strong enough to actually move it. Did you see it jerk a little bit when I turned it on? That's just a magnetic field that I'm putting on that thing. And so this is just an iron, it's steel, but it has a lot of iron in it, that has been magnetized. So we have made it into a magnet. Now,
Can you magnetize yourself since you have iron in your blood?
not enough. No, and yes. In a strong enough magnetic field, it will line up the domains of the iron deposits in your body. Now, I have never seen it done to a human, and maybe it shouldn't be done to a human, but I have seen a video of them doing it to a frog. It doesn't hurt the frog. The frog comes out just fine. It is not squashed when it is done. But it was placed inside a little, very strong electromagnet, and it levitated that frog. So the frog's body was magnetized enough that it was just floating right there, this tiny little space. I mean, it was a little frog. It was about the size of the hole with my fingers. It wasn't very big. So it was a little frog in that area, and it was just levitated right there. All right here I have some paper clips that has enough iron content in it. Now, right now, nothing's magnetized. Not able to pick anything up at all with this. But, let's see. Maybe this one will do it. I am going to set it on top of these right here. And then I am going to literally just bang on those paper clips. Why am I banging on the paper clips? What I've talked about already so far.
Steve,
I have magnetized those paper clips. How did I do it?
Exposing it
By exposing it to an external magnetic field. Why was I tapping on it? Literally to help jiggle those domains so that they fell in line with each other. How can I demagnetize these? I'm going to rejiggle those magnetic domains.
No.
Yeah, I'm just going to hit it. I'm not in a strong magnetic field anymore, so I'm just banging these things around. Now, just a minute ago, I picked one up with the other, right? So let's try it. It's no longer a magnet. I can't pick it up. I have randomly oriented the magnetic domains that were in there. So we have materials that are soft magnetic. They're very easily, those domains are switched so that they line up with each other. And they very easily lose that, become demagnetized. So if we have a hard magnetic material, it's harder to line up these domains, but they are much more permanent. And so they hold their direction much better.
slamming on the ground.
But it would not be good for me to start slamming this on concrete. You're right. It would weaken because I would start randomizing those magnetic domains if I did that. Now, I want you to come up here for a moment and look at these. I have 5 compasses sitting here. Do you notice anything different?
They're all pointing in the same direction.
Number one, they're not all exactly the same direction, but something even more dramatic than that. Yeah, look at these two right here. These are exactly opposite. I have messed up this one. I have reversed the direction of that compass needle is just a magnet, floating so it can line up with the Earth's magnetic field is all it's doing. But I have reversed the order accidentally, but that's what's happened. I've reversed the direction of this magnet. And so it's pointing the opposite way that it should be. The red should be pointing towards the north, and the white's pointing towards the north. Because I have done, there's too many magnets hanging around in my box over here, and so I've messed it up. And this one has been messed up a little bit too, and I don't know why these things are not quite the same, but anyhow. Let me show you something else. Come over here. You can see which direction this is pointing, okay? Generally like that for my north. Now I'm going to bring it over here by this spot, by that file cabinet. Something is magnetic, isn't it?
So what if you're trying to find your way somewhere?
You're in trouble. That's exactly right. These metal file cabinets have parts of them that have been magnetized. Why? They're sitting in the Earth's magnetic field. That's why. So if I am trying to do my orienteering with my magnetic compass and I'm following my map and I actually come across an area that maybe has some lodestone in it, and my compass needle, I wasn't paying any direction, and my compass needle starts pointing in a different direction, you're in trouble. You're exactly right. It's just following the strongest magnetic field that it senses. You can sit back down. Same?
Yeah.
What's that? Yeah, I would need to put them in a magnetic field that's strong enough going in the right direction, and then I could remagnetize it in the direction it should be. I'm going to have you move your Chromebook for just a second, and I'm going to set it. Whoops, you notice something already? Back over here, you notice which direction it's pointing? North is where it should be.
Underneath the table.
That's correct. What's underneath? You've got that middle leg that's right over there. And if you move it across this desk, there you go. Now it's pointing in that direction.
It's not as bad as when you go.
Now it's pointing back more how it should be pointing. So you've got to be careful if you're using a magnetic compass for a direction, because it's going to be influenced by whatever magnetic field happens to be around. So we can make temporary magnets. We want it to be a permanent magnet, probably most of the time. So soft magnetic materials, iron is fairly soft, easily magnetized, but tend to lose their magnetism. Hard magnetic materials, nickel is an example, tend to retain their magnetism pretty well. The strength of a magnetic field often depends on what the material is that it is made up from. So this is a pretty strong magnetic field. That's not magnetic. That's a pretty strong magnetic field. So I can pick up my nice big nail here, and you've got, that's a pretty good pull. So I'll pass it around, and you can put it flat on there and pull it apart so you can kind of get the feeling of how strong that one happens to be. Do I have another nail sitting over here? I don't have another nail sitting over here. So we'll just have to wait on our next example. So just keep passing that around. So what is a magnetic field? The region in which a magnetic force can be detected. We obviously are in a magnetic field because these compass needles are pointing in a specific direction. And I move it around and they point in a different direction. So magnetic field lines are the lines that are drawn that show the direction of a magnetic field, which is the direction that a north arrow would go. So, what can I say? Here, let's do it this way. Notice the direction of the arrow is the direction a north pole would go. So these compasses that are lined up right over here, that red is the direction that a north pole would go. It's attracted to the south. Over here, the red is pushed away from that north, because that's what a north pole would do to a north pole. It would repel it. So why, and this compass is correct, this one is wrong, that red should be attracted to a south magnetic pole. So why is that red pointing north if it's attracted to a south magnetic pole? Because in the north is a south magnetic pole. The red right here is the north pole of this compass magnet. The white is the south pole of this compass magnet. The north side of that compass is pointing toward the north, which means up there in the north is not a north magnetic pole. It's a south magnetic pole. The north end of the compass is a north pole attracted to the north geographic direction. And in the north geographic direction is located a magnetic south pole. So that's why the north pole of the magnet is pointing in the north direction, because there's a south pole in that north direction right up there. So that can be a little confusing until you catch on that it's like, oh, that's easy enough. So geographically, the North Pole is where magnetically the South Pole is. But are they exactly in the same spots? And this is a semi-accurate picture. No, they're not. The magnetic North and South Poles are not in the same location as geographically where the true North and South of the Earth is. They're a little bit different, and they can move. If you ever look at a map that is used for orienteering, for a magnetic compass and finding your way, you will find on the bottom of it the declination, which means how many degrees from true north is geographic true north, how many degrees from true north the magnetic pole is in that location where you are. Now it may be off quite a bit. Right here, my compass needle is going to be pointing off like this. North is really here, it's going to be pointing off like this. But if I walk around the globe to where these two things line up, how you're looking, they're in two different spots. But where I'm standing, they're in line with each other. And so I would have no declination or no error in my magnet or my compass from where it was pointing. So depending on where you are in the globe, your map is going to tell you how many degrees off is it if you're really wanting to use it. All right, so you felt this one, and it's pretty strong. I mean, it's no trouble pulling it apart, right? So is there a difference? And you can pass that one around. So let me back up over here. And the next thing we're going to do, actually come back up here. All right, so hang on to that. David, you hang on to it and bring it up here. So here I have a nice bar magnet that I'm going to put under my piece of paper right over here. And some of you maybe have done this in the past. Some iron filings.
We're going to be on
Like all the little silly guys with mustache.
Oh, okay, so we're just...
So
The thinking cracker barrel.
I dropped these iron filings. I should get something that looks a little bit like this. It's not doing it too great right now.
It's like the SS-50.
They're all jumping over on top of that magnet. You can kind of see some lines, and there you can see some lines right over there. But these magnetic field lines that are direction of my magnetic field, which is the direction a north pole would go. Remember when we talked about conventional current? It's the direction positive would move. So we don't care whether it's an electron that's moving or not. Same thing here. The direction I'm going to draw magnetic field lines is the direction that a north pole would move. All right, you can sit back down and keep passing around that little bit stronger magnet.
It's a thing from Toy Story. Check it out.
Guess I need to see Toy Story. I'm not familiar. Oh, what? How could I not have ever seen Toy Story?
All right, what about the thing from Cracker Barrel where you got the little guy and he it has the iron filings in it? And what you do is you take the little magnetic pin and you draw with the iron filings. I forgot what those are called.
Yeah. Compass needle points to north in a magnetic
The
field.
north pole of a compass needle points in the direction of a magnetic field. To show directions of magnetic fields in drawings and photographs, we use a set of three symbols. A series of arrows shows the direction of a magnetic field in the plane of the paper. A series of dots for the heads of the arrows represent a magnetic field pointing up from the page. A series of X's for the tails of the arrows represent a magnetic field pointing down through the page.
So think of a literal arrow that you would shoot from a bow that has a point on the front, feathers coming off the back. So if I am seeing the feathers, that is going away from me. So if we draw an X, it's going down into the paper. If you have the dot, that's that point of the arrow coming right at you. So that dot, the arrow is going up out of the page. And then if it's going left, right, up, down, etc., then you can just draw the arrow as it is there. So an X means it's going into the page, a dot means it's coming out of the page. So those are the conventional ways that we draw our magnetic fields. Earth magnetic field acts like a bar magnet, but the magnetic South Pole was really at the geographical North Pole, and the magnetic North Pole is near the geographical South Pole, as the picture shows right down there that we already talked about a little bit. So how else can I get a magnet besides having these ferromagnetic materials where the domains are lined up? And that has been my example of all this stuff, are the ferromagnetic materials, and we line up the domains. Well, we have discovered that if I pass a current through a wire, we get a magnetic field. And we're going to use some compasses, and we're going to demonstrate this in a little bit so we can figure out the direction that that magnetic field is going. And then we are going to learn the right-hand rule. So let's look at the right-hand rule right over here. You use your right hand, and you point your thumb in the direction the current is going. Now we need to remember that's conventional current. The direction positives would be going. Then your fingers are going to curl in the direction of the magnetic field. Must be the right hand or it curls in the wrong way. The right hand, and it's going to curl, so my fingers are going to point in the direction the North Pole would want to move. So let's try that out. Keep passing around that magnet. Has everybody been able to pull on that one for just a little bit? So I'm pulling out an old DC power supply just because I don't want to burn up any fuses on my new one. So this one, I don't care. So I can crank it out until it trips the little breaker in here, and then we'll just reset it and do it again. Okay, so you are going to need to come up where you can be at the table and bring your right hand with you. I'll take this off. All right, now this is not going to mess up anybody's electronics. You don't have to worry about that.
Without making a sound.
All right, so bring your right hand with you. I want you to tell me, look at where, here's red, here's positive, here's black, here's negative. I want you to tell me what direction the current is flowing through this wire as it goes over that paper. Which direction is the current flowing as it's going through this wire over this paper? I just need to know the direction. David, you're correct. It's going to go positive to negative, so it's coming this way. So that is I. Now I am going to put a compass right underneath this wire. Now they're iron filings. Something is messing up my compass. Maybe it's just a bad compass. Oh, guess what I had in my hand? I had a magnet over here. I was bringing it close. And I was wondering, what is going on with that thing? All right, so here we go. So I'm gonna turn it. I'm gonna hold it so it's like this. I'm gonna turn it and I'm gonna hold it so it's like this. There we go. So right now I have it like this. If I put my compass on top of this wire, there we go. If I put my compass on top of this wire, what direction is that compass going to go? So my right hand, my thumb is going to be in the direction of that current. So that magnetic field should be curling like this. So on top of the wire, it should be going this direction, towards me, kind of. So let's turn it on and see. Flip that on, and then flip it off. Let's turn it off. Did it go towards me? No. There you go. If I put it underneath that, So here, now my finger's underneath my wire, should be going towards you guys. Do the same thing. There you go. So obviously, when I pass a current through a wire, I have created a magnetic field around that wire. Now if I switch this, right over here, this allows me to do alternating current. Now I want you to do the same thing. Brett, turn it on, then turn it off. Try it again. Turn it off. Notice it kind of floated around a little bit here, but it didn't go in one direction. Why not? Because my current direction is alternating 60 times a second. And so there's no way that that compass needle is going to respond fast enough to flip back and forth 60 times a second. So alternating current, that's not going to happen. So if you take your compass and you put it by the wires that are going into your toaster or something like that, your compass needle is not going to respond to that because that's alternating current. If I've got direct current, then it's going to move. Right-hand rule. You can sit back down. Thank you. Now this magnet is strong enough. Some of you have noticed it's pretty strong. So I need a volunteer to come up here and not slide that off, Brett. Do not slide it off, but pull that magnet off for me.
I can use both hands.
You may use both hands.
I can do it.
And you probably, I didn't notice, but you probably had to try to angle it a little bit trying to get it away. Because going straight on this thing, I mean, it's just not going to come off very easy. Yeah, you bet. See if you can pull it straight. Now it's a little hard to grab a hold of. It's a little slick. But without twisting it in any way, just pulling it straight. Yeah. Right. Yeah. It's a little bit slick right now. Everybody's greasy hands have been on it, so.
Yeah, without bending it up.
Right. Yeah. Now if you twist it, then you can break the hold on it. But just trying to pull it straight.
Just use a lever.
All right. So that one. Okay, Christian, you do it, then we'll move on.
Just use your foot.
I can't grab this thing, so
Yeah, the problem is really grabbing that magnet a little bit.
all right, there you go.
Yeah, and if you turn it sideways, then it becomes real easy to do it. But if you're trying to pull it straight, it's just not going to come very easily at all.
That would be funny if you're the only one who knew how to do it sideways and just all these big dudes just sitting there trying to do it.
Turn in your book to 669 for a bit. MRI. Any of you had an MRI?
Yes.
Yeah. Did they ask you when you went to have your MRI if you had any metal pieces or had been grinding metal, that you might have metal pieces in your eye? Why did they ask that question?
It would mess up the MRI scan.
An MRI machine stands for what? Magnetic resonance imaging. An MRI machine uses very strong magnetic fields. You don't want to have little iron filings that maybe got in your eye from grinding, and then they turn on that MRI machine, and it starts aligning those fields, those little iron filings with the fields, because it can cut up your eye. So that's what they asked me, was that same question there. I want to read a little bit about this MRI, and then we're going to see a little video of unapproved activities with MRI machines. 669. Brett, would you read the first paragraph?
Magnetic resonance imaging, or MRI, is an imaging technique that has been used in clinical medicine since the early 1980s. MRI allows doctors to make two-dimensional images of or three-dimensional models of parts of the body, human body. The MRI in medicine has grown rapidly. MRI produces high-resolution images that can be tailored to study different types of tissues depending on the application. Also, MRI procedures are generally much safer than computerized
Axial.
Axial tomography, CAT scans, which flood the body with X-rays.
So you've heard of CAT scans too. Two totally different technologies. A CAT scan is an X-ray machine. And X-rays are damaging to living cells. And so you don't want to expose yourself to too many X-rays. So CAT scans sometimes are needed, but they will limit the number of CAT scans you will have in a year because it's bad for you. MRIs, magnetism, seems to have no bad effects on the human body that we know of. Just might levitate you. You won't levitate an MRI machine. So let's see how these things work. Chloe, would you do the next paragraph?
A typical MRI machine looks like a giant cube, 2 to 3 meters on each side, with a cylindrical hollow in the center to accommodate the patient, as shown in the photo at front. The MRI machine uses electromagnets to create magnetic fields ranging in strength from 0.5 to 2.2.
And that T is Tesla. We've heard that name before.
These fields are strong enough to erase credit card and to pull hands out of pockets, even across the MRI examiner. Because resistance would cause normal electromagnetic to dissipate a huge amount of heat when creating fields is strong. The electromagnets in most MRI machines contain superconducting wires that have zero resistance.
So an MRI, very, very high currents. Now we know if I'm passing a high current through a wire, there's resistance there and it's going to build up heat. So they mentioned normal conducting wires, it'd be so hot you'd just fry anybody who was in an MRI machine. So we have to have superconducting. Now, I should have backed up a little bit. Electromagnet, I mean, we just did an electromagnet, essentially, when I passed this wire, passed electricity, a current. I need to do a little more from it. Any of you ever made, when you were a kid, a little electromagnet?
I do.
So how do you make a little electromagnet? You just take some wire, and you coil it. Where did my nail go? There's my nail. And you coil it particularly around some iron-containing object. This in itself will create a magnetic field, my coiled wires, when it's going around. Maybe we should talk about the direction of that. Or do we get that a little bit later? Oh, we get that a little bit later. Okay, I'll wait on that. So an MRI machine is going to use superconducting materials, zero resistance. Now, how do I get something with zero resistance? Well, we know that things like gold have very low resistance, but they still have a resistance. There are materials, they generally are compound materials made up of different elements, that when they reach a certain temperature, very cold temperature, called the critical temperature, their resistance drops to zero. They're superconducting materials. And there probably is one of these exploring science things that talks about how superconducting materials work. But they only occur at very cold temperatures. Nobody at this point has a room temperature superconductor. Though several years ago, there were a couple of scientists who produced a paper said that they had a room temperature superconductor. And other people tried to replicate their experiment, never were able to do it. Since then, I believe it was found out that they made it up. So anyway, super cold temperature. So we usually have like liquid nitrogen or something like that that cools these things down. So once you start the current going in a superconductor, it continues going. Doesn't shut down until you warm it up where it is above the critical temperature, and then it will stop on its own. But once you get it going, that thing is going to go. And then you apply more current to it, and you get a very strong electromagnet. So how do we get an image from it? Third paragraph. Cassie, would you read that?
The creation of an image with MRI depends on the behavior of atomic nuclei within a magnetic field. In a strong magnetic field, the nucleus of an atom tends to line up along the direction of the field. This behavior is particularly true for hydrogen atoms, which are the most common atoms in the body.
Johnny, next paragraph.
The primary magnet in an MRI system creates a strong, uniform magnetic field centered on the part of the patient that is being examined. The field causes hydrogen nuclei in the body to line up in the direction of the field. Smaller magnets, called gradient magnets, are then turned on and off to create small variations or pulses in the overall magnetic field. Each pulse causes the hydrogen nuclei to shift away from their alignment. After the pulse, the nuclei return to alignment, and as they do so, they emit radio frequency electromagnetic waves. Scanners within the MRI machine detect these radio waves, and a computer processes the waves into images.
So we put a human body which has atoms in it, and they said particularly the hydrogen atoms, which are in water, and our body is largely made up of water, mass-wise at least. So the atoms will line up with the magnetic field, and they have smaller magnets that will pulse so that they will shift the atoms in your body. And as they turn back, they emit electromagnetic waves at a certain frequency, and they pick it up. And how fast they turn back varies by the type of tissue that it is. So they can distinguish one type of tissue from another type of tissue. And then they just create the image based on the frequencies that come back.
Wait, so then
And you can't move.
And you're supposed to remain motionless, right? Otherwise you're going to blur the image because you're moving the tissues in your body that they're trying to look at.
So
Jonathan?
then, like, for example, if they're looking at an injury or something like that?
Correct. Soft tissue injuries in particular, they can pick it up on an MRI machine very easily.
So what is...
Tore a muscle, tendons.
How can they see it? Like, what makes it show up to them?
So the tissue itself has these atoms that will turn back at different rates depending on the kind of tissue, and the rate at which it turns back sends out a specific frequency. And then they have receivers that receive that frequency. And wherever it came from, then they give it a color or something. So it's an image that's created. It's not really a picture that is sent. It's an image that's created based on the frequencies that are received by the receiver there. But it takes very strong magnetic fields for these things. Nate, to the last paragraph.
Different types of tissues can be seen with MRI depending on the frequency and duration of the pulses. MRI is particularly good for imaging the brain and spinal tissues and can be used to study brain function, brain tumors, multiple sclerosis, and other neurological disorders. MRI can also be used to create images of blood vessels without the surrounding tissue, which can be very useful for studying the circulatory system. The main drawbacks of MRI are that MRI systems are very expensive and that MRI cannot be used on some patients, such as those with pacemakers or certain types of metal implants.
So if you've got a pacemaker, they're not going to do an MRI on you because of the metal in that pacemaker, and you're putting in a strong magnetic field. Or if you've got those metal filings embedded in your eye, they're not going to do an MRI on you either. Our recording.
I don't want to see that.
So what do we do, or what happens if we create a loop of current-carrying wire? We first saw just one piece of wire that was coming across, and we put our thumb, and then we wrapped our fingers around, and that was direction of our magnetic field. So we call it a solenoid when we have coiled wire that's going through here. Well, it can produce a much stronger magnetic field, and the more loops you have, we will later see the formula that the stronger that is going to be producing a magnetic field. So right up here, come back out up here so you can see this lovely demo. So when I just have one wire, my compass underneath that one wire, and we turn on the current. Am I DC? Yeah, I'm DC over here. And we turn on the current. Whoops. Coming after you. I didn't put it on very well. All right. Now, I need to use a different compass because that one is backwards. Let me use this one. All right, so I turn it on, and it moves. It moves that direction. I want you to tell me the direction the current is going through that wire.
Well, the wire.
Through the wire. The wire is going this way, so the current could be that way or this way. Which way is the current going?
This way. Go that way. This way.
That is correct. Notice which way it goes. The magnetic field is coming towards me, so I'm going to have my fingers that way on my right hand, my thumb. There it is. That current must be going this direction through that wire, because underneath, that's the way it's going to go.
This is coming from positive to negative. Why?
Well, you don't know which way it's connected inside there.
Oh,
I'm just connected on two sides. You don't know which way it hooks up in there. Because any two of these that I put together, it will go to different wire loops, depending on which two of these I put together. Now, if I increase the size of the wire, as well as the loops of the wire, well, first, look at the rate, and I'll turn it down. Let me turn it down over here. All right, look at the rate that that needle turns to try to give a rough estimate of how strong the magnetic field is. Okay? Now, not when it's going back, but when I turn it on, you can see, you can watch that thing move over, fairly slow pace. So if I put it under this one, have many more loops, and run the current through this one, what do you think will happen to the speed that that needle goes? That's probably going to happen much faster as it goes over there. So when I have a solenoid, I just have wire that is going around in a bunch of loops. And that is an electromagnet. So here I have wire going around in a bunch of loops. And if I should get away with these magnets here. When I have this setting here, notice there's no effect. This coil and that wire have no effect. Turn it back up again. Turn it on. I've got a little bit going on. Put it down here at the end. Turn it on. We can tell this is north. That's the direction of my magnetic field. We'll have to figure out a rule here in just a minute. If I put a ferromagnetic material in it, or a core, it strengthens the magnetic field. What it does is it concentrates those field lines, so it makes it stronger. Now the only issue here is that is already magnetized. You can see how it's attracting just a little bit. Do you remember which way that red, the magnetic field, went a minute ago in this coil? When I turned it on? It went this direction, didn't it?
Yeah.
You turn it on. Yeah. So I've got a magnetic field in this direction. Now this nail is magnetized already, but it's magnetized in the opposite direction of the magnetic field that I'm about to put through that coil. Nothing will explode. Oh no, did I just flip my... Yep, look at my compass. You see what I just did? I just flipped my compass. Instead of I wanted to flip the nail, but I just flipped the compass. So much for that one.
Wait, so is it just ruined after that?
No, I can flip it back. Since it went that way, I should be able to flip it back. I'm just going to try to change the direction. So let's see if it will do it here. Oh, I forgot to have it. Did I overmute that? I left it on. All right, let me try it again. Let's see if we can flip it back. There we go. We just fixed it. Where's my other battle?
That one needed it the other way.
That one needed it the other way. All right. Well, anyway. So we just flipped that thing around. Now, let me pull this one out. Just a minute before you have a seat. So this becomes an electromagnet, which is simply a magnet caused by electricity passing through, and we can turn these things off and on. So they're nice so that we can pick things up and we can put things down. Oh, but it's going to stay. No, it's not. Good. So I'm going to turn it on, I pick it up, I turn it off, it drops, except that one magnetized a little bit. So here's bigger coil, bigger solenoid. I don't know what it came out of.
She's got these.
This was actually here when I started teaching here, and it was like, oh, that's going to be useful. So I don't know where it came out of.
You just set this in there and shoot.
So no magnetic effect until I turn it on, and then there it goes. Well, now you can see it going real quickly, and you can see the direction that that magnetic field is. So that magnetic field's in this direction. So if I put a paper clip right here, look at that, that's a magnetized one. If I put a paper clip right there, I doubt it will even pick that. No. If I turned it on, ooh, did you hear it in there? It sounds a little bit. Here, let me turn it on when it's sitting there. We'll have to watch.
Like on the staple.
It just vibrated it and moved it to the middle is what you heard as it moved around. All right, go ahead and have a seat. Let's go ahead and stick that on the side. So let's get our rule for the direction in a current carrying loop for our magnetic field.
A common way to create a magnetic field is to create a current in a loop of wire. Remember the right-hand rule for magnetic fields created by currents. If your right hand is here, with the thumb pointing in the direction of current flow, then the curl of your fingers shows the direction that the magnetic field points. The field wraps around the wire, as we have seen before.
So you notice my thumb in the direction of the current. So right here, my thumb would be in this direction. My fingers would curl like this, so they're curling around. That would be the direction of the magnetic field.
Now let's investigate the magnetic fields created by this part of the current loop. Again, point your thumb in the direction of current. The curl of your fingers will show the magnetic field that wraps around the wire at that point. Notice that the magnetic field formed around the other part of the wire was similar. Both magnetic fields point upwards inside the loop and downwards outside the wire loop.
So you see how they're both going up inside the loop? Here's my thumb, here's my current. Inside the loop, they're going up. When I come around over here, there's the current. Inside the loop, they're coming up. So it is coming up, or that's the direction of the magnetic field inside that loop.
The current in every part of the loop helps create an upwards magnetic field in the center. Outside the loop of current, the field points down.
So this acts just like a bar magnet, if you will. My magnetic field is going up, so that's the direction the north would go. So you can do this laborious process of twisting your hand around the loop, but there's a faster way of doing it. Take your right hand again, but this time curl, since we're using a loop, curl your fingers in the direction of the current. So here's my current, there's my fingers curled in the direction of the current. Guess which way my thumb is going? The direction of the magnetic field. So when you have a solenoid, my magnetic field was this direction. So I know the direction that current is going around this solenoid. It's coming around this direction because my magnetic field coming out my thumb right here. So for a solenoid, you just reverse what you do with your fingers and your thumb, and you can get the direction of that magnetic field. There was a next, wasn't there?
Notice that this is very similar to the magnetic field of a bar magnet.
There you go. They're the same. It's like a bar magnet. The same thing happens. I think that is it for my demos. Let me just look around to make sure I haven't missed any demos for the day. Nope, that is it for the demos for the day. So you can start answering questions. Section 1 and 2. You may.